So hello Year 12 and welcome back after hopefully 2 weeks off over the Easter holidays. Not that they would have looked much different to what happened before that, but I hope that you're all well and safe and you've managed to enjoy the warm weather. We're continuing with our revision of the inorganic side of AS level chemistry, moving with the next topic that you did in sequence, which was topic 8, energetics 1. Now this builds very, very strongly on your GCSE content. If you did AQA, that would have been C5, energy changes, endo and exothermic reactions, and bond energy calculations. So let's have a quick look what's in it. So this is the course spec. You need to know that standard conditions are 100 kilopascals and a specified temperature. We normally talk about 298 Kelvin, but that's not essential. But a specified temperature is needed to be known. A random thing that might have slipped through the net, know that the enthalpy change is the heat change measured at constant pressure. Occasionally that is asked. Obviously, we are dealing with temperature changes sometimes when we're working out enthalpy changes, energy given out or taken in, but the pressure must be constant for all of these calculations to work properly. Be able to construct and interpret enthalpy level diagrams showing an enthalpy change, including appropriate signs for exothermic and endothermic reactions. Very similar to what you did at GCSE, only here we're using the term enthalpy instead of energy, and we'll talk about the difference in a bit. For this topic, you don't show activation energy. That's needed for your rates of reaction topic, but not for this topic. Something some of you are terrible at, you need to be able to define the standard enthalpy change of these different types of reaction. Some of you just couldn't be bothered to learn it. Some of you came unstuck in your endotopic test when there was a 5-mark question, and that is a genuine exam question asking you to define the enthalpy of formation and the enthalpy of combustion or something like that. Understanding experiments using Q equals MC delta T, we'll look at that. Evaluating sources of error and assumptions made. Again, some of you really struggling to think about problems with the experiment rather than mistakes that you made. So think back to the previous topic, the difference between error and mistakes. We're looking for sources of error in the experiments. Insulated container, just like the required practical from GCSE. Enthalpy of combustion, measuring that. In a spirit burner, you did that. And we did a couple of experiments where the enthalpy change cannot be measured directly. We did 2 experiments that we'll look at in a sec, but solvation and neutralisation. We used both of those to calculate an enthalpy change that couldn't be measured directly. Calculate enthalpy changes in kilojoules per mole from given experimental results. You need sign and units in the final answer. And constructing enthalpy cycles using Hess's law. Some of you really still struggling to do this. Make sure you can. Calculating enthalpy changes from Hess's law. Once you've got the cycle, most people are fine. Determine the enthalpy change of a reaction using Hess's law. Know the definitions of bond enthalpy and mean bond enthalpy. Calculate enthalpy changes of reaction using mean bond enthalpies, and calculate mean bond enthalpies from changes of reaction. This is very, very similar to what you did at GCSE actually. So let's start with an energy level diagram. Which of these diagrams shows an exothermic reaction? Pause the video, explain your answer, see if you're right. Well, the most common misconception is this. Look, the chemicals absorb energy and so they get hotter. So this must be an exothermic reaction. The chemicals are losing energy, so they must get colder. So this must be endothermic. This is completely wrong. Get this out of your heads. It's totally the wrong way round to think about something, okay? So what is the right way to think about these? Okay, so looking at this energy level diagram here, first things first, let's get rid of the term energy and replace it with the term enthalpy, given the symbol H. Well, what does that mean? Well, that is the chemical bond energy. Okay, so it's the energy stored in the bonds of the chemicals. And if we see that, we can see that the energy stored in the bonds of the chemicals has gone up. Well, if the chemicals are storing more energy, that energy must have come from somewhere. And typically, it comes by taking in heat energy. It absorbed to turn into chemical energy. Your energy change is thermal into chemical. Because of this, because it's taken in thermal energy, it gets colder. And because it's cold, that's when it can absorb energy from the surroundings. So energy moves in, endothermic. In contrast here, we can see that the products have less chemical energy, less enthalpy than the reactants. Well, if they've got less chemical energy, that energy's got to have gone somewhere and it's been given out, again usually as heat. Here we have converted chemical energy into thermal energy. If the system has more thermal energy, it gets hotter. If it is hotter than the surroundings, then it can release heat. It goes out, exothermic. So there we go. If delta H is positive, so your chemical energy is going up, that means heat is taken in. If delta H is negative, your chemical energy is going down, that means heat must be given out. Here's a second common misconception. When trying to explain why a reaction might be endothermic or something like that, a student might say the energy needed to make new bonds is less than the energy needed to break the bonds. And here, the real thing that drives me nuts is this idea of energy needed to make new bonds. That's what really gets me, because you don't need energy to make bonds. This is wrong. Wrong. You don't need energy to make bonds. And here a useful analogy is magnets. You know it takes effort to pull magnets apart. So if you've got a door like the gate, the biology gate here, to open that biology gate, it takes effort. And if you haven't got the right code and the right card, it's quite hard to pull those magnets apart. It takes effort. It takes effort to separate them. But they jump together by themselves. If you put two magnets quite close together so that they are attracting each other, I think you'll agree that they will automatically jump together, north, south, releasing noise, a bang or a clunk. They automatically jump together, releasing energy. And you can see here a poor gentleman finding out that story about magnets jumping together by themselves, not needing energy to put them together. And the same is true of atoms. It takes energy to separate the atoms, it takes energy to break the bonds, but, and this is the key thing that many students don't get, energy is released when atoms join together. Any bond releases energy because it's lower energy than the starting atoms. So bond making is always exothermic. Okay, and do try and remember that. So the correct definition of an exothermic reaction is where the products have less energy or less enthalpy than the reactants. Fine, it goes down in energy, reactant product, because more energy is released when forming bonds than is taken in when breaking bonds. The temperature goes up, so energy is given out to the surroundings. It's important you get this the right way round. The temperature goes up and then the energy is given out. That's why it gets hot. For an endothermic reaction, this is where the products have more energy than the reactants. That means more energy is taken in breaking the bonds than is released when forming new bonds. Because energy has been taken in, the temperature goes down, so energy is taken in from the surroundings. It gets cold and then absorbs energy. You should know something that's hot does not absorb even more heat energy from the surroundings. Similarly, something that is cold does not lose energy to the surroundings. Okay. Using those ideas, this was a GCSE question. Common bond energies. Can you calculate the energy change and work out if it's exo or endothermic? No matter how many times I tell people to sketch out all the things and make sure you don't miss any bonds, people still refuse to do this. But we've got C3H8 plus 5O2 making 3CO2 and 4H2O. Okay, and just mark off the bonds as you've worked them out. Okay, on the right hand side, 3CO2. 1, 2, 3, 4, 5, 6 of these on the right hand side. 1, 2, 3, 4, 5, 6, 7, 8 OH bonds. On the left hand side we've got 1, 2, 3, 4, 5, 6, 7, 8 CH bonds and 1, 2, 3, 4, 5 OO bonds. Oh, but look, there's 2 bonds I haven't accounted for, which you might have forgotten if you didn't draw it out. I've also got 2 CC bonds on the left hand side. So when I do the maths, I will find out that the reactants have 6,522 kilojoules of energy and the products have 6,912 kilojoules per mole of energy. And you were probably told at GCSE just to do reactants minus products. And that will give you the answer, and indeed that's what's happened here. We've got minus 390 kilojoules per mole, so the reaction is exothermic. Let's go into a little bit more detail and see why it's reactants minus products. And for this, let's imagine these poor lemmings. They've been thrown through a trapdoor here, and they know that there's an exit here, but they don't know, because they're trapped underground, should they dig down or should they dig up. Well, what they do know is they can estimate how far below this trapdoor they are, and they also know that the exit is a certain distance below the trapdoor on the outside of the mountain. So what they can actually do is they can work out, well, I am closer to the trapdoor than the exit is, so therefore what I need to do is I need to dig down, and that might get me into the chamber where the exit is. And sure enough, that's how you would complete level 1 of the lemmings. The same is sort of true in chemistry. Theoretically, we could say, well, how much energy is stored in the bonds of the products, how much energy is stored in the bonds of the reactants, and we could do products minus reactants, but we don't know that. We never know how much energy is actually stored in the bonds. What we do know, however, is how much energy is needed to break those bonds and turn the elements into atoms, to atomize all of the products and reactants, to turn them into gaseous atoms. So the energy needed to break the reactants apart into atoms is this. The energy needed to break the products apart into atoms is this. They go up because it takes energy in both cases. Making bonds always takes energy to atomize them. Well, if we want to know the overall energy change, therefore, we can imagine starting with our reactants, like a molly-mod kit, pulling everything apart into atoms and then putting it back together. So we are breaking things apart, so the dissociation energy of the reactants, but then we are putting them back together to make the products. This is the opposite of breaking them apart. So it's actually minus the opposite sign of pulling apart the products because we're putting them back together. So the overall energy change here is the dissociation energy of the reactants minus the dissociation energy of the products. So if I just pull these up, using bond enthalpy data, you will be given mean bond enthalpy data for the bonds in the reactants and in the products. Worth knowing this, the mean bond enthalpy is the enthalpy change when 1 mole of a bond is broken, averaged over many different molecules. Even within one molecule, like methane, breaking the first CH bond has a different enthalpy to the second, third and fourth because of the way the electrons arrange. So by averaging over many different molecules, we get quite an accurate idea as to how much energy is needed to break one of those bonds. Bond enthalpies are always positive, as it always takes energy to break the bonds. I've lost my pointer. Always takes energy to break bonds. The arrows go from the reactant/products to an imaginary situation where all atoms are separated. As ever with this, you need to know the sources of error. Well, the two big errors. The mean bond enthalpy may differ from the true bond enthalpy in the molecule. For example, the CO bond in something like formaldehyde is a very different strength to the CO bond in carbon dioxide. They're not similar. From memory, this is about 800 kilojoules per mole, and this one's only about 750. So substantial differences there. Also, bond enthalpies are measured in the gaseous state, and they may not represent the bonds in liquids and solids. Okay, so bearing that in mind. But here we can see the situation where we're taking SO2 and hydrogen sulfide, we're breaking it apart into sulfur, oxygen and hydrogen, atoms, that's why it's 2O gas, not O2 gas, atoms. And then we're putting it back together, so we're going in the opposite direction to the enthalpy, the bond enthalpy of the product. So again, it's reactants minus products, and same for example 2. You need to know these definitions. The definitions for standard condition, standard state, enthalpy change of reaction, enthalpy change of combustion, enthalpy change of formation. You need to just know them, learn them. Flashcards. This is a perfect flashcard use here. So standard conditions, 100 kilopascals. It's almost exactly, but not quite, 1 atmosphere, which is technically 101,350 pascals or thereabouts. Okay, that is 1 atmosphere, but standard pressure here is 100 kilopascals. That is known as 1 bar, if you care. You don't need to know that, but it's 1 bar, not 1 atmosphere. It's a stated temperature, usually 298 Kelvin, but always has to be specified. Concentrations always have to be 1 mole per decimeter cubed. So when we're doing neutralisation, for example, that is important. And the standard state is the physical state of a substance under standard conditions. Most data tables show the standard state at 100 kilopascals and 298 kelvins. For example, for carbon, the standard state is actually graphite, which is slightly more stable than diamond at room temperature and pressure. So all diamonds are very slowly interconverting back to graphite. Enthalpy change of a reaction. The enthalpy change that accompanies a reaction in the molar quantities shown under standard conditions, with all reactants and products in their standard states. Okay, so what this means is if you've got methane CH4 plus 2O2 methane gas, oxygen gas, going to carbon dioxide gas, and 2 lots of water, must be liquid, standard states, that would be the enthalpy change of that reaction. So delta HR. I could write it so that it is half CH4 gas plus O2 gas going to half CO2 gas plus H2O liquid. And if this is delta HR2, in which case delta HR, let's call that delta HR1, would be twice delta HR2, okay? So the enthalpy change is whatever you define that reaction as. There we go. Enthalpy change of formation. This is a more specific definition. Enthalpy change that takes place when 1 mole of a compound is formed from its elements in their standard states under standard conditions. For example, this one here, making water from hydrogen and oxygen. We are half a mole of oxygen because we are making 1 mole of our product, and that is really important later that you know that definition, that it's making 1 mole of a product. Neutralisation is the enthalpy change when 1 mole of water is formed during a neutralisation reaction. Again, under standard conditions, everything being in their standard states, and this is typically where we do need that 1 molar concentration of the various reactants. So again here, look, slightly unusual. We've got half balancing numbers because we are making 1 mole of water, and that would be delta HN for this reaction. Delta HN, standard states and conditions. Enthalpy change of combustion. Now, unlike formation, which is making 1 mole of substance, and neutralisation, which is making 1 mole of water, this is 1 mole of a substance reacting completely with oxygen under standard conditions, everything in standard states. Okay, so for example, burning 1 mole of ethane here, 3.5 moles of oxygen, 2 excess oxygen, completely. So another way of saying reacts completely is excess oxygen, forming carbon dioxide and water. Right, Hess's law is very straightforward. It basically says that the total enthalpy change is independent of the route taken. So however you get from nitrogen dioxide to nitrogen and oxygen, the energy change will be the same, whether you go route 1 or route 2. So if going directly is exothermic to the tune of 66.4 kilojoules per mole, then hopefully going from nitrogen dioxide to nitrogen monoxide and then splitting that apart gives you the same energy change, which indeed it does. The total enthalpy change for route 1 is the same as for route 2, and that has to be the case. If you imagine a mountain range and one person here gets on a helicopter and flies directly to another peak, and let's say he goes up 20 meters, then another mountaineer going up and down over this pass must also overall go up 20 meters. If not, if that wasn't true, then by going that way and back again, you would constantly be either increasing in height or decreasing in height, which can't be true. So whichever route you take has to give you the same energy change. So let's look at one of the simplest examples, calculating an enthalpy change of formation using combustion data. So first, can you write this equation? Pause the video, write it down. Right, well hopefully you wrote that 3 lots of carbon, graphite or solid, it doesn't matter, plus 4 lots of hydrogen gives you C3H8. We're forming 1 mole. Important there. 1 mole of propane. Everything in standard states, you need to know the standard state. Hydrogen is a diatomic gas. Carbon is graphite solid. If we burn the graphite, we get 3 times the enthalpy of combustion of graphite. If we burn the hydrogen, we get 4 times, because there's 4 of them, the enthalpy of combustion of a hydrogen molecule. And if we burn propane, we get just 1 time, because there's only 1 mole, 1 times the enthalpy of combustion of propane. But what do we get in terms of products? Well, look, if we burn the carbon and the hydrogen, we get 3 CO2 and 4 H2O. If we burn the propane, we get 3 CO2 and 4 H2O. Not surprisingly, the products on the left are the same as those on the right, so we can use this. We can redraw this lot as a Hess cycle. We can burn down the reactants and the products, and it is so essential you get the arrows going in the right way. We burn down a house, we burn down the products, we burn down the reactants to form these. Well, that's great. If I'm trying to find this, all I need to do then is go down this arrow and back up this arrow. So we can use that combustion data. As we said, that was 3 times the enthalpy of combustion of graphite, 4 times the enthalpy of combustion of hydrogen. This is the enthalpy of combustion of propane. So going from here to here, down this arrow, which is the enthalpy of combustion of graphite and the enthalpy of combustion of hydrogen, is the same as going there down here. So that is the enthalpy of formation plus the enthalpy of combustion of that. So we want to rearrange this so that we have the enthalpy of formation is going down this arrow and back up that arrow. That's why these are both positives, because we're going with the arrow with those enthalpies of combustion, but we are going in the opposite direction of the enthalpy of combustion for propane, so that's why that's a minus arrow there. If we put these in, feel free to work this out yourself. I'm just going to give you the answer that the overall enthalpy change is minus 103 kilojoules per mole. This is Dr. Butterworth's slide reminding you of using enthalpy of combustion data. You will either be given the enthalpy of combustion data or asked to calculate one value. Combustion data is always negative. In contrast to the bond energy data, combustion always releases energy. We can determine it, and we'll look at this in a sec, using Q equals MC delta T. Arrows always go down. If you can remember, write O2 to show that you're using oxygen to burn this. Obviously, you cannot burn oxygen. The enthalpy of combustion of oxygen is 0 kilojoules per mole. And we'll look at those errors in a sec. Right, we can derive, you've just seen, and we've just done one example of how we can derive standard enthalpies of formation from combustion data. And the standard enthalpies of formation, these are the really powerful ones, because these allow us to work out the enthalpy change for any reaction. So let's imagine this reaction. Iron oxide and carbon monoxide forming iron and carbon dioxide. This obviously goes on in the blast furnace. Well, we can imagine building the reactants from elements. We can also imagine building the products from elements. And not surprisingly, we would need the same elements, same atoms, to build both the reactants and the products, right? Products, atoms are conserved in chemical reactions. Sorry, no atoms gained or lost. So we'd have to use the same building blocks for the reactants or the products. Unlike burning down the house, we need to build people up. So build up chemicals, build it up, dyno trucks. If you ever watched that, I have small kids, so I'm very familiar with dyno trucks. Okay, we need to build it up. The arrows go up from the elements to the things that we are building. So on the left, we can see that we need to form 1 mole of iron oxide and 3 moles of carbon monoxide. On the right, we need to form 3 lots of carbon dioxide and 2 lots of iron. So we can actually begin to use this data. And again, we can see that starting from the elements, building the iron oxide and the carbon monoxide, and then reacting them together would give you the same energy change as going up this arrow. Of course, we're interested in delta RH, so going from left to right is the same as going against these values, taking them apart, and then putting these values together. We're going with the arrows, so that's why these values are going to be the same as their initial values, whereas these are going to be minuses because we're going against them. So plus, plus, minus, minus. Don't forget, these values themselves could be plus or minus. So we could have a minus, minus, a minus, plus, a plus, plus, or a plus, minus. And you need to be really careful with your signs. Here are the formation values. Feel free to have a go yourself. I'm just going to go straight into the answer, which is this. So look, here we've got plus minuses. So this enthalpy of formation of carbon dioxide is a negative value, but we are going with it, so that's why it is a plus minus. But in contrast, this here, this is a negative value for the enthalpy of formation, and we're going against it, so that's why you've got a minus minus on this stage. So just be careful, okay? Don't make mistakes. It's all too easy to make sign errors when doing these. And back to Dr. Butterworth's slide, enthalpy of formation data. Write the elements underneath. Ensure that the elements are in their standard state, okay? You must give state symbols. You must make sure hydrogen is, for example, H2, oxygen is O2, okay? Arrows go up towards the reactants and products. This is the opposite. You burn things down, you build things up. Delta HF of elements is naught. Of course, the definition is making things from the elements. So if you've got elements, the enthalpy change is 0. And that's why on the previous slide, the enthalpy change of iron was not listed, because that has 0 enthalpy of formation. Because you're starting with iron, you're ending with iron. Some substances such as water in their standard states, but given off as a gas in some reactions, particularly combustion, may be a source of error. Okay, so let's go forwards there. Here's some for you to have fun with if you wish, absolutely up to you. Those are the answers if you did. Now let's look at those practicals. The first practical you did involved a polystyrene cup, and you were trying to work out the enthalpy change of the reaction of CuSO4.5H2O solid dehydrating to give you CuSO4 solid and 5H2O liquid. Now, the problem with measuring this enthalpy change directly is you need to heat it really strongly on a Bunsen flame to make this happen. And trying to measure a small energy change when you are heating something extremely strongly is very, very difficult. So you actually found this enthalpy change in a different way. First thing was you put some copper sulfate into water and you measured the energy change there. Now, if I want common misconception 3, it is about this value m. The value m is not the mass of copper sulfate you put in, it is the mass of the thing that you are measuring the temperature change of. You are measuring the temperature change of the water, so therefore this must be the mass of the water, not the mass of what you put in. And despite telling some people over and over again, they're still putting the mass of the chemical in, not the mass of the thing they're measuring. But here's an example. Let's say with copper sulfate, you've got a rise in temperature of 4.7 degrees Celsius, mass in kilograms, 4.18 joules per Kelvin, kilojoules per kilogram per degree C, and that would have given you an enthalpy change of, an energy change of plus 0.49 kilojoules per mole. If you put the mass in kilograms of the water, then you will get the answer out in kilojoules. If you put it in grams, you'll get the answer out in joules, okay? But let's remember, okay? Now, here's the thing. If you've got water that is heating up, that is because the chemicals are releasing energy. So the water gets hotter because the chemicals have lost energy. And this is why it's minus Q over N. So the energy that went into the water has come out of the chemicals. So minus Q over N, the number of moles, will give you the enthalpy change per mole. For the hydrated crystals, so these were the white ones, these ones were the blue ones, and actually what you found was this energy change was slightly endothermic. The water got slightly colder. Again, it's the mass of the water that's really important, because that's what you're measuring the temperature change of. And that would give you an energy change that's negative. If that's negative, of course, it means that the energy going out of the water is going into the chemicals. So the chemicals are absorbing energy, going up in energy, divided by the number of moles, which when you did it was about 0.150, and you would have got an endothermic reaction. And we can put that into a Hess cycle like this. We can imagine, we want to know the energy change of this reaction. This is what we are trying to measure. So we can imagine dissolving both of those, solvating both of those. We've calculated the energy change for that reaction, and going left to right is the same as going down this arrow and back against that arrow. So it is delta HR minus this one, because we're going in the opposite direction. That was 11 kilojoules per mole. That was minus 65. So 11 minus 65 plus 76 kilojoules per mole. What were the major sources of error? When you did this, your value would have been less than 50%. of the actual value, a huge difference, a huge error. The main sources of experimental error. Have a think. Can you get 3? Okay, the ones you should have picked up is you are losing or gaining energy from the surroundings. Normally a loss is more significant, but it's energy transfer to or from the surroundings. Okay, that's why we use a polystyrene cup, but it doesn't make it completely not happening. Okay, there is still some heat transfer. Approximating the specific heat capacity of the solution. The method assumes all solutions have the heat capacity of water. That's probably not a bad assumption, but if you're going away from water, so things that are more sticky or gloopy or different liquids, then that certainly is a problem. I'd say that this was potentially a problem. Neglecting the specific heat capacity of the calorimeter. Some energy is absorbed by the apparatus, by the polystyrene cup, by the thermometer. Reaction or dissolving may be incomplete or slow. So this was certainly a problem for you guys, that not all solid reacted or dissolved. And therefore that's going to really affect your answer. And density of solution is the same as water. That means we can equate 50 centimeters cubed to 50 grams. May not be true, but these are the big ones. Energy transfer from the surroundings and the fact that not all the solid might dissolve. Try and remember those. For the calorimetry experiment, you filled something with water, a copper calorimeter with water. It was copper to allow good heat transfer into it. You heated it up, you measured the energy change, you measured the difference in mass, so mass of fuel burnt. And then you measured the temperature change. Careful, some students forget they measure it to start with the lid on and then without the lid, and they get a much bigger mass change than they would expect. Again, Q equals MC delta T, but it is the mass of the water because you are measuring the temperature change of the water. So let's say 100 centimeters cubed, 0.1 kilograms, gives you number of kilojoules. The number of moles of ethanol, the mass lost. So here we presumably burnt 0.45 grams of ethanol, which gives us that number of moles, and minus Q over N, because the energy that went into the water came out of the fuel, gives us an energy change of minus 1374 kilojoules per mole. Again, thinking about how this would be put together, well, we might want to know the enthalpy of formation for ethanol, in which case we can burn ethanol and we get that value that we've just measured. We can either burn the hydrogen and the carbon ourselves or look up data values and work out the enthalpy of combustion of 2 lots of carbon, 3 lots of hydrogen in excess oxygen. Enthalpy of formation down there, up there, so it's going to be 1646 minus 1646, sorry, minus, and the enthalpy of combustion there, minus 1374, and that gives you an answer of minus 272 kilojoules per mole. You should be able to get 3 really big sources of error in this practical. Have a think. The main one, just as it was before, energy losses from the calorimeter, okay? So this is once the calorimeter is heated up, it is losing energy. This is a serious problem. There's a similar one, which is incomplete transfer of energy. This is the fact that the energy from the flame didn't all go into the calorimeter to start with, and this was a serious problem, especially if your flame was not positioned correctly. You could see the flame, it was yellow, therefore the fuel was combusting incompletely. Less important ones, evaporation of water, evaporation of fuel, it's still hot, you might get a bigger energy mass difference than you'd expect. The heat capacity of the calorimeter not included, measurements not under standard conditions, water being a gas. But the big ones I would say were the top 3, energy losses, incomplete combustion and incomplete transfer of energy. Okay, so almost finally, let's have a look at your CPAC, and that was to investigate this particular reaction. That was the thermal decomposition of KHCO3 solid being heated to give you K2CO3 solid, potassium carbonate, plus water, liquid, plus CO2 gas. Yes, I know when you thermally decompose it, it actually gives you steam, but we always need to talk about elements in their standard states. So clearly 2 of these give you 1 of those, 1 H2O and 1 CO2. But the problem, as before, is because we are heating this thing so strongly, it's very difficult to measure the temperature change of the reaction while you've got it in the oven. So what we need to do is we need to do it a different way. And in this way, you reacted the potassium carbonate with hydrochloric acid and the potassium hydrogen carbonate with hydrochloric acid. You measured the enthalpy changes of those reactions, and then you could work out the original one. So that was the equation for the thermal decomposition of KHCO3. Construct an energy cycle to link this with the 2 reactions, neutralising those things. Have a go. I'll show you the answer. Okay, so you've got KHCO3, 2 of those solid being heated. This is what we want to know, to form K2CO3 solid plus H2O liquid plus CO2 gas. Right, now if you take these and you put these in HCl, you are going to get 2 KCl aqueous. And what else are you going to release? You're going to release CO2 gas. You're going to release 2 lots of those. And you are also going to release 2 lots of water. Okay. If you react this with hydrochloric acid, again, you're going to end up with 2 lots of KCl. This is going to generate 1 lot of H2O and 1 lot of CO2, but that's okay because the other lot's here that is just not being changed. So that's where they come from, okay? And this is the Hess cycle. Now, we can measure the reaction of KHCO3. So this is 2 times the enthalpy change of reaction for the first one, because we measured the enthalpy change of 1 mole of this reacted with hydrochloric acid. This is just 1 times delta HR2, and therefore if we want to know what the enthalpy change is going from left to right, we're going down here against that. So it's 2 times delta HR1 minus, we're going in the opposite direction of this arrow, delta HR2. And lots of people forgetting that we needed 2 lots of that, because when you measured the enthalpy change of reaction, you measured it for 1 lot of potassium hydrogen carbonate falling apart. Very final slide. Here we go. I'm just going to flash all these up. These are 4 out of the 5 different ones. You got a bond energy one earlier on, but you can see all the different things they can throw at you. They can give you formation data and ask you to work out the enthalpy change of a reaction. This is very common. They can give you combustion data and ask you to work out the enthalpy of formation. This is a very common one as well. And in particular here, notice this is products minus reactants. This is reactants minus product. And that's because here you build up, but you burn down. For neutralisation data, this is another example of using neutralisation data to get an enthalpy change of reaction. And up here, this is one of the practicals you did. This is using reaction data to get another reaction data. It should be fairly straightforward. You just need to practice these things to get good at them. Just be meticulous and careful with your working. I am going to check the first set of work you're doing. So there's going to be a question sheet, multiple choice questions, and as before half term, there's going to be a quiz online for you to fill in your A, B, C and D answers. It'll self-mark and it'll just check that you are doing the work. Other than that, feel free to email me if you've got any problems, and I shall see you at the end of the week when I give you some longer answer questions. Bye bye.